So I'm very happy to introduce today our speaker, Sariel Har-Peled. He is truly a man who doesn't need an introduction, and therefore I'll just let him speak. There goes my 15-minute speech. Sariel, please go ahead.
Thank you, Boris. So this is a joint work with Ben Reichel, who is in UT Texas in Dallas, and Elliot Robson, who is currently my PhD student, and the mandatory screen. So I should say that this is a more applied work. Hopefully, there are enough interesting ideas to keep you engaged. And I have a website, fréchet.xyz, where you can see all the stuff about this paper, animations, examples, and so on and so forth. And I should say up front that because it's more applied work, a lot of the idea I'm going to discuss are, not our ideas, right? At some level, in the sense that there are our ideas, but they are present in the literature before. So let's talk about the Fréchet distance to people that don't know this. So you're given two polygonal curves, and the task at hand is to compute the similarity. And the regular way it's being described is that you have two starting points. One of them, you have a person walking along one of the curves. On the other curve, you have a dog walking along the other curve. They are allowed to move only forward, and they try to synchronize their motion such that the maximum length of the leash is minimized, right? And this is the measure. It's a maximum bottleneck measure. The similarity, the Fréchet distance between the curve is the maximum length leash one needs. And so this was studied originally by Alt and Gadou in the context of curve similarity. And they presented, all the curves I'm going to talk about are, by the way, polygonal curves. And they presented essentially a quadratic type algorithm. It was very complicated using parametric search, etc., etc. Those things were simplified since, but I think it's fair to say that there are currently no simple algorithm for computing the Fréchet distance, and quadratic time is believed to be the best one can do in the worst case. And there is a huge amount of work on this Fréchet distance in the literature, various extensions, implementation, etc., etc., etc. Okay, so because the continuous version of the problem is difficult, people looked on the discrete version, which is really what most people use in practice. And the basic idea is that you sprinkle points on the two curves, and now you think about it as two frogs. One frog jumps along the one sequence of the points, the other frog jumps along the other sequence of the points, and in every point in time, only one frog is allowed to jump forward, and of course, the frog is not allowed to jump backward. So if you turn it into dynamic programming, this turns out into a very easy dynamic programming, very similar to edit distance. Okay, now what is the problem with the Fréchet distance? So this animation hopefully can show you the problem, and this was computed by computing the discrete distance, discrete morphing, and extending it to continuous. Okay, so I should say, by the way, that I call this matching, continuous matching between the two curves. I'm going to refer to it as a morphing, and hopefully you see the problem here. The leash at some point gets very long, and then it stays long because the algorithm cares only about the maximum length. So once this happened, it stays long, right? Which is really not quite what we want. In particular, here's another example where we are matching the two curves on the left. And on the right figure, you can see a morphing, two morphing, in fact. So this is a profile. So what is a profile? A profile is just I show you in every point in time what is the length of the leash. And think about it as the x-axis being parameterized from 0 to 1, or the length of the two curves. And as you can see, those two, you have a morphing here where the leash becomes large and then keep being large, while the other one becomes much shorter. And under the Fréchet distance measure, those two things are equivalent, right? And somehow this is, not quite, doesn't quite feel right. Okay, so this work, we're going to give a more nuisance definition of Fréchet distance. In particular, I'm not really only going to care about the distance itself, but I'm going to care about the morphing, how the morphing look like. And hopefully I'm going to present simpler and better algorithms. And we implemented our algorithms that are available as packages in Julia and Python. And those are official packages, but that's, I mean, that you can easily install them from the package managers in those languages. I will talk about this later. And there are various ideas and problems that came out of trying to implement this algorithm. Okay, so the standard way to think about the Fréchet distance is via the free space diagram. The basic idea is that you take one curve and you straighten it, and you put it conceptually on the x-axis. You take the other curve, you straighten it, and you put it on the y-axis. And now you look on the configuration space, which is just going to be a point in the rectangle, where a point in this rectangle corresponds to a point being placed on one curve and the other point being on the other curve, at the location determined by the x and y coordinates. The two curves are being uniformly parameterized. And what you see on the right is how this function, this height function look like. By this I mean that for every point in the rectangle, we have the associated location of the 2 points, and the height is going to be just the Euclidean distance between those two corresponding points on the curves, right? So you get this function, two-dimensional function. The function has this very nice grid-like structure, where every grid cell corresponds to one segment in one curve and a segment in the other curve, and the function inside the grid cell is just the distance for points on the two curves. Here is a different look on the right side. You can see it as a terrain, right? You just from the side. And the task at hand is essentially you want to find a path from the bottom left corner of the rectangle to the top right corner of the rectangle, such that if you think about it, so the curve that you're searching from the bottom left to the top right has to be x and y monotone. And you want to have the property that if you interpret it as a walk on the terrain, the highest point you go through is as low as possible. Right? So this is the computational task. And here is the morphing in this case. So you can see this is the optimal morphing, the optimal Fréchet distance. And as you can see in this case, you really want to stick to the curve, try to stick to the shallow areas where the blue areas where the distances are very short. And that's how it goes through, right? And the reason why we get this animation on the right is because, we move the point along the curve on the left, and that corresponds to this moving segment between the two endpoints on the two curves on the right. Okay, so the first idea is this, is that instead of doing the smooth globally, right, somehow looking on this graph as a global structure, I'm going to look at it as every grid cell separately. Now, if we look on a unique, on a specific grid cell, then the function there looks essentially like a paraboloid, right? And the important thing is that the paraboloid and along an edge of this grid cell, this function have a unique minimum, right? So if you look at a grid cell, there's going to be, on every edge of the grid, there's going to be a unique point of minimum, excuse me. And then what we do, we connect those points, but we connect them only locally. We connect only those portal points inside the grid cell, creating a click. And furthermore, we connect them only in a way that we move forward, right? So every grid cell is going to have two incoming portals, and we have two outgoing portals, and we're going to connect the incoming portal into the outgoing portals using a click, okay? And the edges are going to be directed, right? Now we have this graph, and we have vertices. This graph, if you think about this graph is very similar to a grid graph, right? Essentially, to identify a vertex, you don't need to identify the edge it belongs to. And we have a left vertex, bottom left vertex, a right topmost vertex. And now, important property is that the function inside every cell is convex. So the motion planning inside a grid cell, the most natural thing is to do just a straight line. You go from the portal to the next portal, just follow the edge in a straight line. So, and the maximum height is going to be realized by either the start of the edge or the end of the edge. So essentially we have heights on the portals or height of the vertices. And in this graph, we are looking for the path from the source to the target that minimize the maximum height of the path, okay? So we have a directed graph. It's easier conceptually to think about it as the edges having height, it doesn't really matter. And we want to compute the path from the source to the target that minimize the maximum weight edge, right? So it's a min-max edge. And in this case, it can be solved easily in quadratic type. And notice that this is a very simple, again, the graph that we have here is implicitly defined, and it has a very predictable structure, so we can compute it on the fly. You don't really need to compute the graph, so it's very easy to solve it directly. Now, okay, so the resulting algorithm is very simple, right? So you just compute this this path in this DAG, directed acyclic graph. Now, one problem is that the path that we computed might not be monotone, but notice that it's almost monotone. And what do I mean by it's almost monotone? Because of the way we structured the graph, once the path that we compute crosses a grid line, it never crosses it back. So, or in another way of saying it, during the morphing, if the morphing goes over a vertex in either curves, it never goes back. So it might go back and forth, but when it goes back and forth, it's always a situation where you move forward in one of the curve and you move back and forth inside an edge of the other curve, right? You zigzag either inside a column or a row of the diagram. So it's almost monotone. And we have to solve this bottleneck shortest path problem. And it turns out that for general graph, you can just do essentially Dijkstra, which is a good idea to do because Dijkstra is easy to implement. Or it turns out that Gabo and Tarjan have a very nice algorithm that in fact can do it in m log star m. If you want to read the beautiful algorithm, I recommend it. It's a very nice algorithm. Now, I would like to say that this idea of looking on the portals and looking at the edges and doing this bottleneck shortest path, this idea is really not that new, right? So if you look on the original paper by Alt and Gadot, they looked on the undirected case, and they looked on the same graph, but now it was undirected. And on this undirected graph, they computed the bottleneck shortest path. This gave them the weak Fréchet distance. Now, for the undirected graph, the bottleneck shortest path can be easily computed by computing the MST. And then for any 2 points in the graph, vertices in the graph, the bottleneck shortest path is just the unique path in the MST. So so you readily get quadratic time algorithm. So really what we are doing here is the same algorithm, except that we are using this directed graph. Okay, but we want something that is better, right? Because minimizing the bottleneck, the maximum is not enough, right? We want something better. So you want the retractable Fréchet distance or retractable morphing. And intuitively, what it is that we would like to walk the dog, but we have a retractable leash that always try to be as short as possible, right? So, and the idea is to define it recursively, right? So what do I mean by that? You have the vertices S and T. Assume that you have a directed graph. All the edges have unique weights to keep things simple. You find the bottleneck shortest path, right? So UV is the edge that is the bottleneck. And now what you do, you recursively compute the bottleneck shortest, the retractable path from S to U, and then you compute the retractable shortest path from V to T, and then you put it together, and this is the retractable path. And unlike the bottleneck shortest path, the retractable shortest path is uniquely defined, assuming that the weights are different. And this makes way more sense for the Fréchet distance, right? So here is an animation showing the two things in action, and the bottom one is the retractable version. And as you can see, the retractable version essentially stops and wait until the leash gets short again, and only then it starts moving forward, while the regular Fréchet morphing, once it hits the maximum, sticks with it, right? So hopefully you believe that the bottom one is better. And one nice thing about it, which is hopefully demonstrated by this simple case, is that now we can talk about portion of the matching that are good, right, and portion of the matching that are bad, right? We can say, you know, there are parts of the matchings that are, the matching is very tight, and then there are those parts that are, the matching is very large, which are bad, and we can throw them away, we can write them as outlier, do something about them, which we could not have done before. Now, so it turns out that computing the retractable part, right, this can be done by a very minor variant of Dijkstra. So the basic idea is that you have your set of vertices you already visited, and you always pick the shortest edge coming out of those vertices already visited, and you add it to your current set. So it's essentially, you just run Prim's algorithm on this directed graph. A critical property of this algorithm in practice, as is Dijkstra, is that you stop early, right? Once you arrive to the target vertex, you can stop. And that makes a huge difference in practice, because in practice, you don't really have to explore the whole grid. In practice, you have to really explore very small portions. Now, I should say that this definition of retractable Fréchet is not ours. It was defined by Buchin et al. Earlier. They called it locally correct. And they presented different algorithm that seems to have not realized that you essentially can just use Dijkstra for this. So maybe I should, before going into what's written on this claim, I should say that this is already hopefully kind of nice, because we can now, the algorithm essentially is, you compute a simplistic graph, you run Dijkstra on it, and you get this Fréchet distance, this retractable Fréchet distance. It might not be monotone, we will deal with that shortly, but the algorithm to compute it is very simple. Now, as this, and the important observation is, of course, that this retractable Fréchet, so we call it, by the way, Vertex-edge Fréchet, because we are using the portal on defined by an edge of one curve and vertices on the other curves. So, by the way, from this point on, all the morphing and all the Fréchet I'm going to talk about are going to be retractable. That's kind of the default thing. So the nice thing is that computing the retractable Vertex-edge Fréchet is very easy. You're essentially running Dijkstra on this implicit graph, right? It's very easy, and you get continuous morphing, right? You get this Fréchet distance, and it's easy to verify that this quantity that you get, the maximum leash, is bounded from above by the real Fréchet distance. And the reason for that is very simple. You can just take the morphing, the path from that realizes the Fréchet, the real Fréchet distance in the free space diagram, and map it to a corresponding path in the graph. And the corresponding path in the graph is going to be only better as far as the leash, but it might not be monotone anymore, which, as I said, we will deal with that. Okay, here's an example of this non-monotonicity. Essentially, as you can see, the non-monotonicity either happen in the free space diagram, either in a row or in a column, because you are moving back and forth. And the question, of course, is what to do about it, because we really want monotone morphing. So the first thing is to implement stand your ground, right? So never go back, right? So you take the curve and you start moving along it, and you just never allow yourself to go back to in the diagram. So you keep going forward only, and this is very easy to compute in linear time, right? So this is brute force monotonization. You can do it in linear time. And the nice thing about it is that now if we computed it, we have two numbers, right? We have the leash length according to this weak Fréchet distance, this vertex-edge Fréchet distance that we computed, and we have the distance provided by the monotone morphing, and this gives us the interval. And we know that the optimal Fréchet distance must be in this interval. Now, if this interval happens to be of length 0, we are done. We found the Fréchet distance, and that happens a lot, right? Because what happens a lot is that the non-monotonicity is usually very far from the bottleneck points in the morphing. So you make it monotone, and the bottleneck didn't change, and you're done. You found the Fréchet distance between the curves. So that's nice. But of course, what happens if this does not happen? So the second idea is that you introduce vertices, right? So the idea is that if we introduce more vertices into a polygonal curve, it doesn't change its Fréchet distance from another curve, right? I just split an edge. It has no effect whatsoever on the Fréchet distance. But on the vertex edge distance, it has an effect, because what you do when you introduce a vertex, you are splitting a column or splitting a row, right? So the basic idea is that you look on the morphing whenever it goes back, whenever you have an edge where you're having this back and forth, you just put a point in the middle of the zigzag, and you split the edge. You do it along the morphing. This splits the two polygonal curve for both polygons, and then you recompute it, right? And the effect is, as you can see in the bottom here, is that the zigzags become smaller, right? And you can repeat this process. This process had very few vertices. So, you repeat it like 3 times, the zigzags are already pretty small. And, you do it a few more times, and essentially it's already hard to see. And then, of course, if you really want a monotone morphing, you just do the brute force monotonization on that, and you're done. And that gives us a very natural algorithm for computing the exact Fréchet distance, while this vertex edge distance is smaller than the distance we get from the monotonization. We refine the curves by putting points on where the morphing zigzags. We recompute the vertex edge Fréchet, and we repeat. And as I said, this process very quickly isolates the bottleneck and works reasonably well in practice. Now, I should say up front that we are taking a very pragmatic view of things in this work, because it's implementation oriented. So when you implement algorithms in practice, you're going to have floating point issues. that's going to be a major concern, and there are not really such things as floating points. You know, there are no such thing as exact algorithms. Exact algorithms exist only if you're willing to do exact arithmetics, which is in most of the cases insanely expensive as far as running time, and you don't want to do it. So in particular, we're going to take the very pragmatic view that if I get an approximation of 1. Whatever 001, it's good enough. I'm going to consider it as being exact. Okay. Now, I guess I mentioned it already that the tractability is important, right? It enables us to detect those the points where the matching is bad, discover outliers, and so on. And let me emphasize again is that the algorithm to computing this retractable Fréchet is very simple. And in practice, you would just compute it, do brute force monotonization, and you would be happy with the result. You would not worry about too much about other things. Okay, so let's move to the next stage. Next step. Okay, so I want to speak about a low-level sub problem that we encountered. And in this sub-problem, we are given a polygonal curve and a segment, and we would like to compute the Fréchet distance between the segment and the curve, right? So this problem, as I would show you hopefully later, shows up a lot in the implementation if you want fast running time. So in practice, you want something that runs in linear time and is very simple. And in this case, this is very easy, right? You just compute this retractable Fréchet, right? A vertex-edge retractable Fréchet. In this case, the free space diagram is just this one column. So you just have to go from the bottom to the top, and you just compute the portals, and you compute their heights, and you take the maximum, and that's your retractable distance. And now what you do, you just take this morphing and you make it monotone, right? And what we prove is that this is a tree approximation. Right? And I believe, by the way, that this is true in general, right? I believe that if you take the retractable Fréchet morphing and you monotonize it, you always get a constant approximation to the regular Fréchet distance. Okay, now let's speak about simplification, right? So in practice, we are going to speak about curves that are, with tens of thousands of vertices, and you don't really want to do the computation on the, on the curves themselves. You want to reduce the complexity by reducing the number of vertices, and so you want to simplify them, and there are well-known simplification algorithms that preserve Fréchet distance. There is this work of Aaron et al. That shows that you can do simplification, and the idea is that you give me the threshold, and the simplification algorithm is going to pick subset of the vertices, and it does it in a greedy fashion. What do I mean by greedy fashion? It picks the start vertices as the start, and then it goes as far as it can with a single segment. It picks the furthest vertex it can, such that the segment still provide a good approximation in the Fréchet distance to the subcurve it matches. And you continue in this fashion, right? You always pick the vertex furthest away. You must pick to keep the error threshold, and you continue in this fashion, and that's it. So this gives you, in practice, this algorithm works great. It gives you a high quality approximation, but it's a bit slow. I will talk about it a bit later. But that's kind of the basic strategy. So now I want to approximate the Fréchet distance between curves, right? And the basic idea is that if I have a morphing, right, I have a continuous matching from one curve to another, and I have another matching between the B and C, I can use the triangle inequality. I can get the morphing between the two curves. so we can chain more things, which suggests a very simple algorithm, right? You start with some silly upper bound on the Fréchet distance between the curves, and then what you do, you have this radius r, which would be your simplification radius. You simplify the two curves to this within this arrow parameter. This gives you two simplified curves. And then what you do, you compute the Fréchet distance between those two simplified curves. And this immediately gives you, by chaining those morphings, you get a morphing between the original curve and the target curve. And furthermore, you can compute how much, the morphing, not only the morphing gives you, the matching, it also gives you, of course, the maximum leash, so you know the distance. And it gives you an interval where you know that the real Fréchet distance must be inside this range, right? Now, so you get an upper bound and a lower bound, which is roughly the simplification radius times 2. And you look at the ratio. If the ratio of between the upper bound and the lower bound you have is small, then you return the approximation, you know that it's good. Otherwise, you take this parameter d, and you shrink it by a factor of 4, and you repeat this process. And it works, this is very simple. It works very well in practice. I'm kind of oversimplifying things, but that's the basic approach. Okay, what about the exact algorithm? The exact algorithms, we want to use simplification, but you have to be way more careful, because you want to simplify the curve in such a way that the bottleneck is preserved, right? The idea is that the areas that you don't care about, because they are far from realizing the bottleneck, you can simplify them quite a bit, but areas that are critical, you should not touch them, right? So this basic idea leads to a fast algorithm. There are many details making this kind of things work, but I want to give you the kind of the basic idea. So the basic idea is that you start with some approximation. It can be a very low quality approximation. And what this approximation gives you, it gives you a morphing between the two curves. So you get the profile on the right. The profile on the right, to remind you, is this any point in time in the matching, what's the distance, what's the length of the leash. And we care about the maximum, right? And since it's an approximation, not only we get the maximum, we also get the lower bound, which is that we know that the exact distance must be above this lower bound. And now the idea is to look at this profile and observe that all the vertices were doing this morphing. If they have leash that touches them and the leash is much shorter than the lower bound, then you can move them. Or if you want, you can delete them. You're allowed to move them quite a bit. That would not really affect the Fréchet distance, right? So that's what you do, right? You essentially, for every vertex on the two curves, you mark by how much you're allowed to move them, and then essentially you do this sensitive approximation, right? Where you move things only if you're allowed to, right? And this is what you get in this case. And you can see here that the left part, which is really, the leash is very short, get quite simplified. While here, this part, which is critical, essentially the simplification leave the curve as it is, right? So now you have those two simplified curves, and you compute the Fréchet distance, and you repeat the process. But importantly, now because you have simpler curves, you can do better job of approximation, so you get a much better lower bound on the Fréchet distance. And you repeat the process, right? You again do the simplification. Notice that the simplification now is really being sensitive only about on a much smaller area, because we have a much better lower bound on the Fréchet distance. And then you can do it again, right? And once you do it again, you're done, right? And if you look at the simplification here, literally here, the only thing that is being preserved is the bottleneck vertex here and the curve that realizes it in the other curve. right? And that's it, right? And that gives you an exact algorithm. Then, there are a lot of other details how to do it. There are a lot of tedious, it's not good for a prophet to be too specific, but when you write a program, you have to be very specific. So there are a lot of details, but of course, I'm not going to talk about those low-level details here. Okay, let me check the time. Okay, so let me tell you about some questions and shticks and tricks that arises from the implementation. So one issue that is kind of interesting is that we wanted to have a simplification algorithm that is very fast. So what I mean by very fast, I'm allowing you to do some pre-processing, but after I do the pre-processing, I can ask queries and give me a simplified curve below a certain threshold, but the running time should be linear in the output size, right? And the reason why we don't care about the quality too much is because we are speaking about monstrously large inputs. As I said, tens of thousands of vertices. So, and if you simplify it, if you get a simplification with 100 vertices instead of 50, it doesn't matter because you can now take this simplification, this low quality simplification, and you can run the greedy simplification algorithm to get high quality simplification. So what is the idea? It turns out that you can do something very similar to this Dubkin-Kirkpatrick hierarchy, right? So you take your curve and you connect the two vertices, the first and the last, by a segment. This is called the spine of the curve. And you compute the Fréchet distance between this curve and the spine, right? You get the number. Right? Now we take the middle vertex. By middle vertex, I mean the middle vertex as far as, in the index. And conceptually, we now think about approximating this curve by going from the first vertex to the middle vertex, then going to the end, right? And now we compute the Fréchet distance between the red curve and the subcurve it corresponds to, and the blue segment and the blue subcurve it corresponds to. I get two numbers. I take the maximum, and I store this number in this middle vertex. Now, as far as implementation, what is going to happen is that I'm going to have an array, and I'm going to just in the array put this number, right? Now we repeat this process, right? We take every subcurve, we find the middle vertex, we compute the Fréchet distance on both sides, we take the maximum and we write this number for this vertex, and we do it recursively, so we fill the array. Okay, and this takes n log n time if we are using this fast matching between a subcurve and a segment. Okay, now, if you give me a threshold, you want an approximation, all we are going to do is essentially we are going to do the same traversal of this array in the same top-down way, where essentially we are going to collect all the vertices where the label is larger than our threshold. And formally, we have to do something, we have to go one level further down, doesn't matter. And you collect all those vertices and you connect them along the curve, and you're guaranteed that this curve, the resulting curve, is indeed the desired delta approximation, and the running time is, as I said, linear in the output size. So it's a very simple, very fast simplification algorithm. Okay. Now, in practice, what happened for the task we handled, you have a lot of repeated queries on the same curve, so it makes sense to cache the simplifications. And in fact, for every curve, you maintain a hierarchy of simplification of the curves in different resolutions. And it really helped with execution time. And in general, it's a good idea if you're going to have a database of curve and do a lot of these tasks. It's a good idea to do this kind of caching. Okay, let me tell you a little bit about the implementations. So, we implemented this algorithm in Julia. So Julia is this programming language. I don't know if you have ever heard of it. It's what they call high-level programming language. By high level, it means that when you write the code of code for it. It in a lot of cases look like pseudocode essentially. So the feel is very similar to Python, but unlike Python, it doesn't have a lot of the stupidities of Python, like the tabbing and so on. Unlike Python, it's typed. So, by the way, I should say this Julia is a much more recent language than Python. So, of course, they learned a lot from lessons from Python. It's as type as you want, so you can specify types as you can add types information as you write the code, and the program, the program is checked for types. So it's up to you, which is a big advantage. It has a built-in package manager, and this is of course true also of Python. So let me talk about this because for people that don't play with implementations a lot, this is a huge thing. So so essentially what happened is that there is this official repository of packages. You can write your package that does whatever you want. You upload it to the repository. The repository does a lot of checks that your code is up to spec. The format is the right, the directory structure is the right, blah, 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 blah. A lot of those checks are automatic. And then it adds it, right? If they think if it all seems good, they add it to the official package manager. And then what happens is that once it's in the official package manager, you can literally install the package typing one line. You essentially just says, add this package, and it installs it. And you can start using it. And the amazing thing is that, most of the time it just works. And this is a very open model, right, where everyone can contribute whatever they want. But because of this is the official package management, it's really very usable, and it's a very open model. This is to be distinguished from, example, the Sigel model. Sigel is this geometric library in C++ where you have very strict things, guideline what you can do, and a package you write, has to be past the Sigel inspection and so on. And I don't want this to come across as criticism of Sigel, but this monolithic approach has the problem that it's less open. And I think one of the big reasons why Python is so amazingly successful is because there's so much packages and libraries out there. Almost anything you want to do that is reasonable, somebody already implemented, and you can just use it. And Julia has the same thing. One nice thing about Julia is that you get source code of everything, right? So when you install a package, it's download the source code. It's very easy to go and look on what you can literally says, where is the package on my computer, and go and look on what the package does and how it's implemented. It's extremely useful to make sure that they're doing the right thing and also learn the language. Now, unlike Python, this Julia is compiled on execution. So whenever you run it, the compiler takes the whole program, all the packages it uses, everything, and compiles it. And it essentially uses the fact that the compilers now are so amazingly fast that it can do it in, you essentially don't feel the time it takes. And one nice thing about Julia is that it's designed for multi-threading and distributed computing. So it's very, it's very modern. Okay, now as far as Fréchet distance, there was this ACM 6 spatial cap programming competition in 2017, where they designed various data sets and inputs, and they had various submissions. So people, in fact, tried to implement Fréchet distance and tried to pass their tests. We used, as a comparison, C++ implementation by Brinkman et al., which is a few years later, which is even more optimized. They claim to be faster than all the earlier implementations. Right. So let me talk a little bit about our experiment. So there is a huge amount of data available, that real-world data available. So there is a SIG special data from the competition, but there is also GeoLife. This is Microsoft data set where people just walked around with GPS, and there is character recognition set, and there is a huge amount of tracking information for birds, and so there is really no lack of real-world data. And the task at hand is essentially you get this database of curves, and you get a list of pairs of curves, and for every pair of curves, you need to decide whether the Fréchet distance is below or above a certain threshold, right? So here you can see the number of pairs, it's in the hundreds of thousands of pairs that you have to compute the things. Of course, curves repeat themselves. And the running times here shown are in seconds. So frankly, I was very surprised that the Julia was that fast. So the Julia is quite competitive with the C++. It slightly loses for the SIG spatial data. It's twice slower on the characters dataset, but for the GeoLife dataset, it's 4 times faster than the C++. So, and the reason is because the GeoLife data is GPS tracks that are not simplified. So the fact that our algorithm use simplification is really pays off big time. Now, the last column, Julia MT, is just because this task is really repeating the same task a large number of times. This here, this is the multi-threaded implementation. So in Julia, it's very easy to turn implementation into multi-threaded, and that's what we did. That's what you would do in practice, and when you have to handle such a task. It required some work to make the code multi-threaded, but it was in the half an hour amount of work, not much more than that. While doing multi-threading implementation in C++ would be a nightmare. And as you can see, the running times are pretty amazing. Okay, here are some example inputs, that specific input that we use to get more informations. This is the Julia results on those inputs. The only thing I want to emphasize is that, we tried some monstrously large inputs, right? Tens of thousands of vertices. And the columns are the approximation. And you can see that, for rough approximation, we get amazing running times. While the exact running time are still pretty good. This is the exact algorithm with the simplification. So you still get pretty good running time. On the other edge, if you try to do the Vertex-edge Retractable Fréchet with non-simplification, for some of those cases, you hit the quadratic running time. And in particular, for the large input, we were not able to get the running time. Now, we also, Elliot also implemented the algorithm in Python using a package called Nambla, so which is a way to get around Python's slow running time. You essentially have this library and it compiles the code. And you get also pretty amazing running times, although in general it is slower than the Julia code. Okay, future research. So I think one interesting thing is to try and handle things like noise and outliers, which I think with the retractable notion becomes much more natural. And another interesting problem is to try and do things like consensus curve, right? I give you a bunch of curves that try to be, I don't know, bird flying for, airplane flying from airport A to airport B, and you kind of try to figure out what's the curve that describes their motion, all of them together at some level. And I think that that those kind of problems are quite interesting. And I hope that people would use this library, because now that they are available as official packages, it's in fact pretty easy to just install them and start playing around with those things. And that's all I had to say. Thank you.